Here's an example from section 3.9, finding a linearization. So we're going to consider the function f of x equals the square root of x. First thing we're going to do is find the linearization of f of x at a equals 49. So we've got our linearization formula right there. L of x equals f of a plus f prime of a times x minus a. Okay, and we are given our value for a. So L of x is going to be f of 49 plus f prime of 49 times x minus 49. So you can put that in right off the bat there. And then we'll find the values that we need. So f of 49 is just going to be square root of 49. That's the positive square root, so we get 7. And then we're also going to need the derivative f prime. Let's start with f prime of x. Okay, so f of x is just x to the 1/2 power. So f prime of x is going to be 1/2 x to the negative 1/2. That could also be written as 1 over 2 square root of x. So that makes it a little easier to plug in 49 there, to rewrite it with that radical, because you'd get 1 over 2 square root of 49. So that'd be 1 over 2 times 7, which is 1/14. Then you stick those values on in. So L of x is going to be f of 49, which is 7, plus f prime of 49, that's 1/14, times x minus 49. And that's our linearization function. Okay, I guess I can squiggly underline that for our answer there. Okay, now if you were just finding the tangent line of f of x at 49, you could also come up with this answer. It is just referring to the linearization there. So this is just doing that tangent line basically in point slope form. Okay, now we're going to use our linearization here, use the linearization of f of x to approximate the square root of 50. So what we have here is we want to approximate the square root of 50, which would be f of 50, all right, equals square root of 50. And so we are looking at an x value of 50 here. And if we want to approximate that f of x value, we can use L of x instead, because the values of f of x and L of x are close to one another near our point of interest at a equals 49. Okay, and we're pretty close to that. So our square root of 50, aka f of 50, is approximately equal to L of 50, and we could plug that in to our linearization function. L of 50 equals 7 plus 1/14 times x minus 49, so that would be 50 minus 49. Okay, that'd be 7 plus 1/14. Okay, 7 and 1/14 there, or if you put that in a calculator, that would be about 7.0714-ish. All right. So that's what we come up with from the linearization. We could do up to here by hand, which is kind of nice. 7 and 1/14, that would be the exact answer there for the linearization value. And so the square root of 50 is close to 7 and 1/14, close to 7.0714. And it turns out if you just type in square root of 50 directly, so directly, since we can do that with this function. The square root of 50 to 4 decimal places is approximately 7.0711. And so we can see that the direct square root of 50 value and the value, the approximation that we got through our linearization are really actually pretty close to each other. So that is only off by, let's see, only off by a very tiny amount, 0.0003. Which is not too shabby. That's 3, what would that be? Tenths, hundredths, thousandths, 10,000ths. So 3 10,000ths. That's pretty impressive for just using a linear function to approximate that square root. All right. Now, this next one, part C here, has a little typo right now. I'll make sure to fix that for your guys' notes because we don't want to do the exact same problem over again. This was actually meant to say 60, the square root of 60, us to approximate that. So we're working with a different x value this time. And so we'd go through a similar process here. The square root of 60, we're trying to approximate f of 60, and we'll try to do that by using the linearization L of 60, which we can plug in and do most of it by hand here again. 7 plus 1/14, and now that would be 60 minus 49. And so the exact answer for that linearization value would be 7 and 11/14, or approximately, if we want to round a little bit there, 7.7857. Okay. Now, if we check this one out versus the direct value for square root of 60, if you plug that in directly, okay, the square root of 60 out to 4 decimal places turns out to be about 7.7460. Okay, so here we can see that even though the values are still kind of close, it's not as close as it was with square root of 50. We're definitely off by more than 3 10,000ths here. So it's not quite as good of an approximation. So we've got a larger difference here. Okay, larger difference. And the reason why that is because we've moved farther away from where our linearization was set up. The linearization was set up at a equals 49, or an x value there of 49. And so 50 is not far away from that at all. It's 1 unit away. Okay. 60 is significantly further away. And so the point here is that the farther you get, so the farther you get from where your linearization is set up, so from x equals a, or here, the farther we got from 49, okay, the less accurate your linearization is going to be. So the less accurate your linearization becomes. Okay, so if you wanted to approximate, say, the square root of 60, but in a more accurate way, you would set up a new linearization at a different point, probably at a equals 64, the next largest perfect square value there. So that you would end up closer and having a closer approximation for that value x equals 60, or a little little far away from 49 there. So you could set up a new linearization to get more accurate. Now in part D, does this linearization, the one at a equals 49, does this consistently overestimate values, underestimate values, or neither? And the fastest way to tell this is to think of a graph of what's going on. So let's sketch our function here, which is the square root of x. F of x equals square root of x. And if you just make a really kind of generic square root curve, it would look something like that. F of x equals square root of x. Let's say arbitrarily that a equals 49 is about here. Sure. I'll even put that in quotes because you know it's not to scale. Okay. And so remember that our linearization is basically referring to the tangent line to that function at that point. So let's sketch in that tangent line. Okay, there it is. So there is L of x. And from the graph, we can see there, because of the way that line is tangent to the square root curve, that L of x is consistently larger or having larger y values than f of x does. So L of x is consistently greater than or equal to f of x. The point where it's actually equals is at 49 itself. That's where the two come together. They touch at that point. So that gives us the result here that L of x is going to be consistently overestimating because the values are always a little bit too large. Okay, overestimating. We can also see from this graph why the square root of 60 turned out to be less accurate than square root of 50. Because if we think of where 50 would be on this, it's very, very close to 49. So our f of x and L of x values are really, really close to each other at that point. So that would be like where 50 is approximately. And then 60, you might have moved over to about here, let's say. And you can see that there, the f of x and L of x values are significantly farther apart. So the approximation really is not quite as good there. Okay, so that just kind of clarifies again why the approximation doesn't stay as good the further away you get. So yeah, but L of x is overestimating, and that is why. So there's our first linearization.